We will continue with the topic of chromatography. Chromatography is the most important downstream in bioprocess because it can help one to separate and purify proteins. It can be used for separating and purifying the metabolites and very small molecules, peptides and so on actually. So chromatography is the most important in downstream, and that is why we are also going to spend several classes in the area of chromatography. And as I talked about before, there are different types of chromatography, and we have been slowly spending more time on each one of them. Chromatography is like ion exchange, chromatography is like hydrophobic interaction, then chromatography like size exclusion or gel permeation. So we shall spend some more time on this gel permeation chromatography. It is also called size exclusion chromatography because it is based on size. It is almost like a filtration because filtration is based on size. It separates small particles from large particles using a medium. Same thing happens with the chromatography of gel permeation chromatography as well. So it separates small molecules, that means small proteins from large proteins based on the size. So what do you have here in this particular setup is you have porous matrix, and there are pores are present in the solid. So small molecules like small metabolites or small proteins or small peptides enter this porous matrix, whereas the large ones, that means large sized molecule or large molecular weight molecule, do not have any interaction with the porous matrix, so they start travelling faster. So you will find large molecules or large molecular weight compounds coming out first, whereas the small ones are entrapped inside this porous matrix, so they take much longer time to come out. So you separate proteins based on their size. The big ones come out first, the small ones come out later. So this is how it works. If you look at this picture, you can see that a mixture of the large and the small proteins are fed. The small proteins start interacting with the porous matrix, so the large proteins come out first, and then later on you collect the small proteins, that is the small molecules. So this is the principle of gel permeation chromatography. So generally we use Cefadex gel type of column. It has got a polysaccharide dextran cross-linked to form a 3-dimensional network in the shape of the beads. So they are always in the shape of a bead, and it has got a 3-dimensional network and a lot of pores are there. It is a highly polar because you have several hydroxyl groups present inside. The higher is the cross-linking, the pore size becomes smaller, lower is the cross-linking, the pore size is large. So we can control the pore size by modifying the cross-linking. So when I control the pore size, I can use it for different types of filtrations. Okay. So basically what happens here, you have small molecules entering inside the porous matrix, and the large molecules do not find access into the pores, so they just travel down the tube. So the total volume of a column of a gel, so if you look at the total volume, there are many parameters one needs to consider. So the total volume of a column of a gel is made up of 3 volumes: V0, Vi and Vj. Vg is the volume occupied by the gel particles. So the gel particles are actually occupying certain volume, but you need to keep in mind when the solution is flowing in, the gel gets swollen. So the volume occupied by the gel when it is really dry vis-a-vis the volume occupied when it is inside the column when it is swollen will be very different actually. So Vg is one term. Next term is Vi, that is the pore volume of all the particles, because as I said these Cefadex beads or gel are highly porous, so that will also have certain volume. And then interstitial volume, that means the volume we have which is not occupied by the gel particles, we call it external void volume. or exclusion volume. So there are three terms here: the volume occupied by the interstices between these beads, the pores present in the beads, and the volume occupied by the gel particles. So all these three make up the total volume of a column of a gel. Okay. Now typically this V0 as I said, that is the interstitial volume, is about 33-35% of the total volume of the packed column. That is the external porosity. It is of the order of 30-33-35%, that is what it is actually. Whereas if you look at Vg, that is volume occupied by the gel particles, that will be about 20%-30% of this Vc, that is the total. Okay. So the remaining is what is the pore volume actually. Now if you look at the volume occupied by the mobile phase will be occupying all these empty spaces, that is the V0 plus mobile phase will also be present inside the pores, that is the Vi. So the total volume of the mobile phase inside the column will be V0 plus Vi. Vg is the actual volume occupied by the gel particle. Okay. So one needs to have some idea about what is the swelling capacity of the gel, what is the volume of the pores, and what is the packing density. So all these parameters will affect my total volume of the column. So as I said, the gel when it is dry will have certain volume, and when it is swollen, because of water or solvent coming in, it will have another volume. So that swelling part comes into the picture actually. So how do you measure that? You can do it experimentally in the lab. You can take the gel particles, you can dry it thoroughly in an oven, and then see what is the volume occupied by that. So that is one way of looking at the gel volume actually. Okay. So the water or solvent regained is defined as the grams of solvent taken up by 1 gram of zero gel. Zero gel means the gel does not have any solvent, that means it is very dry. So if the dry weight of the gel is not known, then the inner volume may be calculated by substituting the value of Vg, that is Vg is the volume occupied by the gel particles when it is completely swollen, by the density of the swollen state. Okay. And the density of the gel in wet state is determined by an instrument called a pycnometer. So one can find out what is the density when it is in the swollen state, and we can find out the volume occupied by the dry particles by completely drying these gel in an oven and then looking at the displacement of water or some other solvent which does not allow the gel to expand. So that will give us an idea about the volume occupied by the gel in a dry condition. There is something called elution volume, that is the volume of the elutant required to elute a compound. So what do we do in a gel permeation chromatography? We inject our solute in the feed at time equal to 0, and then we are adding an eluent. So the solute travels through the column and finally it comes out. So the elution volume is the volume of this elutant required to move the solute from the inlet injection point right to the outlet. So now this depends upon so many factors. It depends upon the interaction between the solute and the gel particles, it depends on the volume of the interstices, it depends on the volume of the pores and so on actually, and in fact that is what this particular relationship is going to give you. So the elution volume V is a function of distribution coefficient. Distribution coefficient is like partition coefficient or the interaction between the solute adsorbed vis-a-vis the solute present in the liquid phase. So the elution volume VE is given by V0 plus Kd into Vi. V0 is the void volume as I said, or interstitial volume, okay, that is the excluded volume. Now Vi is the volume of water outside the gel grains, that is the pore volume. So you have solvent present in the interstices, solvent present inside the pores, right. Now those are the two terms coming in, V naught and Vi. Now there is a term called Kd. Kd is something like a distribution coefficient, that means distribution between the inner volume and the outer volume. Kd indicates fraction of the inner volume accessible to a particular compound. So Kd depends upon the geometry of the column, it depends upon the geometry of the packing and so on actually. So Kd can be large, Kd can be small, Kd can be 0, Kd can be 1 and so on actually. Depending upon that my left hand side varies, that is the elution volume. So this equation tells you what is the volume of eluent required to elute out a solute from the inlet to the outlet. Now this is a function of two volumes, V naught, that is the outer volume or the void volume, and Vi, which is the pore volume, and there is another term called Kd, which is the distribution coefficient. Now Kd depends upon the geometry of the column, geometry of the packing and so on actually. So for different values of Kd the elution volume can change. So Kd can be 0 or Kd can be 1 or Kd can be in between 0 and 1 and so on actually. Now selectivity of a gel filtration medium cannot be adjusted by changing the composition of the mobile phase, okay. So in a gel filtration, unlike your ion exchange or reverse phase type of chromatography, we cannot change the selectivity pattern by changing the medium, because the gel filtration depends upon the size of the solute, it does not depend upon any other parameter, just the size. So by changing the composition of the medium we cannot change the selectivity pattern. If you want to change the selectivity pattern we have to change the beads, we have to change the porosity of the beads, we have to change the pore volume of the beads, that is the only way. Whereas if you take other chromatography like ion exchange or reverse phase chromatographies, I can change the composition. For example, if we take ion exchange chromatography, I can change the ionic strength of the medium, thereby I can either enhance the interaction of the solute molecule with the stationary phase or I can reduce the interaction. Same thing with reverse phase, I can change the hydrophobicity of the solvent carrier medium, and by changing that I can enhance the interaction between the solute and the stationary phase, or I can reduce the interaction. Whereas in gel filtration we cannot do that, because gel filtration is based only on the sizes, it is almost like your normal filter medium, okay. So gel filtration is based only on the size, so the interaction happens between the solute and the stationary phase gel. So the stationary phase gel means the size of the gel, the porosity of the gel, the pore size of the gel material. So that is a very important difference between a gel filtration or a gel permeation or a size exclusion chromatography vis-a-vis other types of chromatography like ion exchange or reverse phase chromatography. Okay, let us again go back to this particular equation where we said elution volume is a function of the pore volume and the interstitial volume and the term called Kd, that is a distribution coefficient. Now if we rearrange the equation we get Kd equal to Ve minus V naught by Vi, okay. Now there could be three different situations one can consider, okay. If the molecules are very large, that means the molecules cannot enter the pores and it is completely excluded from the gel, so we can consider Kd is equal to 0. So that is the situation where molecules are very large. So if Kd equal to 0 then Ve equal to V naught, that means the eluent volume will be exactly equal to the interstitial space, that is all, because your solute does not interact with your solid phase material, that is solid gel. Now if you have very small molecules then Kd is equal to 1. In that case we have Ve equal to V naught plus Vi. Now V naught is nothing but the interstitial space and Vi is your pore. So this is the total volume occupied by the continuous phase solvent. But generally we may have Kd varying between 0 and 1, okay. So Kd can vary between 0 and 1. In that situation your eluent volume will vary between V naught and V naught plus Vi. Okay, if Kd is very large, is greater than 1, then what will happen, then adsorption of the compound and the gel will occur, okay. The compound will get adsorbed, then it will not get desorbed, okay. This gel filtration is just doing a filtration job, it is not doing an adsorption process, one needs to keep that in mind. So gel filtration is only acting as a filtration equipment, it is not acting as an adsorbent. So we do not want Kd very large, greater than 1, if it is so then the solute gets adsorbed on the gel, then it is almost like a adsorption column rather than a gel filtration column. So generally we will have these three situations, Kd equal to 0, that means for very large molecules the molecules are completely excluded from the gel, Kd equal to 1, that is very small molecules, so they are accessible, completely accessible to the gel pores, then we have Kd between 0 and 1, so that is the general case. So in each case we will have the volume of the eluent required in terms of V naught, that is the interstices or the void volume, and in terms of Vi, that is the pore volume, that means the volume occupied in the pores, okay. So for achieving a complete separation of the components in a given mixture, the sample volume to be applied is limited by the differences in the elution volume of the solutes, okay. So you need to keep that in mind. Okay, now suppose I have a 2 component mixture, so I have a mixture containing 2 components, 1 and component 2, okay. So I should know what is the elution volume for component 1, I should know what is the elution volume for component 2, and that difference is called the Vs, and that is what we should apply for achieving a separation, okay. So Vs, that is the sample volume required, will be the difference in the elution volume of the solute 1 and 2. So if the elution volume for solute 1 and elution volume for solute 2 are almost equal, then your Vs will become very small. What does that mean? That means we are not able to achieve a good separation, okay. Vs becomes very small actually. If the elution volume for component 1 and elution volume for component 2 are very vastly different, then this difference also increases, so Vs also becomes very large actually, okay. So but then you need to again consider points like flow irregularities, the packing has not of the gel is not homogeneous, there is a lot of heterogeneity there is going to be diffusion limitations and so on. So instead of achieving a good separation like this, we may end up with a separation like this. So here you can see there is a overlap in these 2 places, and you are going to have impurities of component 1 and component 2 happening here, whereas if you look here they are very good separation here actually. So we need to consider what is the elution volume for component 1, we need to consider what is the elution volume for component 2, and if they are vastly different then we can achieve good separation, but then you need to consider the other heterogeneities of our column packing, heterogeneities of the flow, irregularities, diffusions and so on actually. So all these factors make your system non-ideal, and you may end up with the overlap of these 2 components, and whereas you would like to achieve like this. So imagine if you have a mixtures of several components, each one having different elution volumes, you may end up having lot of overlaps of several of these peaks. So you need to do quite a lot of trial and error optimization so that you get good separations of the various components in your GPC or gel permeation chromatography. Now I mentioned that Kd is a function of the size and the shape of the gel and also the type of solute and the type of the tube which we use and so on. So this particular plot tells you how does the molecular weight of the protein behaves as a function of Kd for different shapes. So if you have a spherical shaped material, so logarithm of molecular weight and Kd will appear like this, whereas if your protein is like a coil, then it will appear like this. If it is like a rod, that means one of the dimensions is much smaller, whereas other dimension is very large, then you are going to have a relationship of this form. So the logarithm of m versus Kd will appear like this, okay. So generally if the proteins are spherical in shape, you are going to have your linear range in which you can operate, where the logarithm of molecular weight and Kd could be linearly varying in this range actually. And if it is a spherical coil and then rod, the relationship or the type of graph changes quite dramatically. So generally we can take the middle range, which looks quite linear, okay. So this range you can develop a relationship between log m and Kd of this form, Kd equal to a minus b log m, okay. So this is a linear relationship, and we can calculate a and b if you have certain standard graph. Now b depends on the width of the pore size distribution of the column material and the value of intercept, and alpha is a function of b in pore size actually, okay. So b depends on the width of the pore size distribution of the column material, and the value of intercept alpha is a function of mean pore size. So because of the shape of this curve, generally we like to operate only within this region, because within this region only you have linearity. So this becomes almost 0.1 to 0.9, this is the range at which we work. Now here alpha is equal to VE2 by VE1, okay. Now there is some parameter called resolution, that is resolution. If you have two components, the resolution is the separation of these peaks of these two components. Now this resolution is given by this particular relationship, alpha minus 1 by 4 alpha k dash plus k dash square root of n, okay. So resolution will be doubled if the number of theoretical plates n is increased by 4 times, because you have a square root of n, which is n, where n is the number of theoretical plates, okay. By if you keep alpha and k dash constant, it is obvious from this relationship we can tell, if I keep alpha and k dash constant we will be able to increase. K dash is nothing but the capacity factor actually. So resolution may be improved by increasing alpha or k dash. So we can achieve maximum resolution by keeping k dash between 1 and 5. So this particular equation tells you how I can improve the resolution, either by increasing my theoretical plates, or I can increasing the capacity factor, or I can modify the ratio of the elution volume of 1 and 2, that is component 1 and component 2 actually. Now we need to know a relationship between the size of the molecule or the size of the protein which you are eluting out with the molecular weight, okay. So generally it is in this particular form, Rg, that is the radius of gyration of the solute, and m is the molecular weight, and alpha is the exponent term, and that depends on the shape of the molecule. So if alpha is equal to 1 for rod shaped molecules, it is 0.5 for flexible coils and 0.33 for spherical molecules. So you can see that although the size, that is the radius of gyration, increases with the increasing molecular weight, it is not all the time a linear increase, but it depends upon the shape. If the shape of the molecule is like a rod, then alpha will be 1, that means Rg equal to m. If it is like a flexible coil, alpha is equal to 0.5, that means Rg is equal to proportional to square root of m. Okay. If it is like a spherical shaped, then Rg will be proportional to m raised to the power 1 by 3. So depending upon the shape of the molecule, the radius of gyration changes as a function of molecular weight m. So the shape of the molecule may be obtained by comparison of hydrodynamic measurements based on intrinsic viscosity, or we can do sedimentation studies, or we can do diffusion coefficients, and then try to get the radius of gyration from light scattering experiments. So the radius of gyration is proportional to viscosity radius of spherical solutes and flexible polymers, but not to that of rigid macromolecules. Okay. So if you have viscosity radius of spherical solutes of spherical polymers, then that will be proportional to the radius of gyration, but if it is a rigid macromolecule, we cannot use that term actually. So what are the materials used in gel filtration? We can use a cross-linked dextran, Cefadex, as I mentioned before, it is a highly hydrophilic. Then we can use agarose, Cepharos, we can use polyacrylamide type of gel, we can even use porous glass gels. Now each one of them have advantages and disadvantages depending upon the type of system which we are studying, depending upon the operating conditions, we change the gel material. Cefadex is stable between pH 4 and 10 and also between 0 to 30 degrees, that is why most of the applications we use Cefadex. It is unaffected by dilute acids or bases, but of course concentrated acids will hydrolyze the glycosidic linkages. Sometimes toluene or phenol or chloroform is also used while soaking, because you want to avoid bacterial growth in wet conditions. So a little bit of this preservative will help in reducing the bacterial growth. So different types of materials and each one of them have certain range for separations based on their molecular weight. So if you take Cefadex G10 up to 700 Daltons globular proteins, we can use it, and if it is dextrans, it can go up to 700 Daltons. If you take another type of Cefadex, that is called G15, we can go up to 1500 Daltons globular proteins. Go to 25, we can work between 1000 and 5000. If you take a G50, it can work for a 1500 to 30,000 Dalton protein. If you go to G100, we can work for 4000 to 150,000 Dalton protein. If you take G200, it can work in the range of 5000 to 600,000 Dalton protein. If you take Cepharos, then it can go up to very high molecular weights, it can go even up to 20 million Daltons. Okay. And if you take Cepharos 6b, it can go up to 4 million Daltons. So you see, by selecting different types of Cefadex column, we can change the operating range as against the molecular weight. So depending upon the type of system which you are trying to study, the molecular weight, we can select different types of column. So the volume of the packed column is a measure of column capacity, and generally the sample volume should not exceed 5% of this column volume. Okay. So if I add too much of sample volume, I am going to have complete saturation of the packing, I may have even diffusion actually. The sample should not be viscous, because if it is going to be highly viscous material, your continuous phase will not be able to transport this sample. Separation depends on solute molecular size and not on the eluent composition. You can use buffers which do not affect structure and biological activity of the solute, that is very important. So if I have to use buffers, I should see that the buffer does not affect the structure and the activity of the solute, because the whole concept of size exclusion chromatography is based on shape and size. We do not want to disturb the shape and size by adding buffers which affects that. The ionic strength of the eluent also very important, because that ionic salts present should not again affect the protein present inside the separation system. So what are the other important features of GPC? Solvent is the most important component in my GPC. It should be dry, so we can use argon, nitrogen or helium, and again it should be degassed in some application. Sample and the continuous phase solvent should be made from the same material actually. We use a light scattering type of detector. The solvent should be filtered. Common solvents which you use are tetrahydrofuran, that is THF, or toluene. Increasing the column length will enhance the resolution. Increasing the column diameter will increase the capacity of the column. So if I want to increase capacity, I will increase the column diameter. If you want to increase the column resolution, I will increase the column length. But then if you have too long a column, there is going to be diffusion taking place and there is going to be spreading taking place. So the peaks may be separating, but the entire chromatogram will be very dispersed and there will be overlap. So where do you apply these? Gel permeation chromatography or gel filtration chromatography or size exclusion chromatography. It has got several applications: fractionation of proteins and other water soluble polymers, gel permeation chromatography, analysis of molecular weight distribution of organic soluble polymers. So I can study synthetic polymers, I can look at the molecular weight, polycarbonate, polyurethanes. Size exclusion chromatography, I can use it for purification and analysis of synthetic and biological polymers, proteins, polysaccharides, nucleic acids and so on. So you see, I can use it for fractionating protein and what other water soluble polymers. I can use it for analyzing the molecular weight of synthetic polymers. I can use it for purification of synthetic and biological polymers, protein, polysaccharides. That is why it is extremely popular, these GPC or SEC or GFC, and it finds application everywhere in protein purification, protein chemistry, in normal organic chemistry labs, in polymer chemistry lab, and in downstream processing lab and biochemical engineering lab and so on actually. So size exclusion chromatography can also assay protein tertiary structures because it measures the hydrodynamic volume. So we can differentiate between folded and unfolded versions of the same protein. So a folded protein, unfolded protein, both will have different volumes, hydrodynamic volumes, and we will be able to separate out. For example, apparent hydrodynamic radius of a typical protein domain might be 14 angstroms in a folded state or 36 angstroms in the unfolded state. So you can get a very good separation of these two proteins. It can also help separation of two forms. Folded form will elute much later because it is of smaller size, whereas the unfolded form it is a larger size, so it will come out faster. So we can develop a standard graph between log molecular weight as a function of elution volume or retention volume time. Okay. So the graph will look like this: as the molecular weight goes down, the retention time or elution volume increases. Okay, so you have known molecular weight material compounds injected. Now they commercially you will be able to get known molecular weight of synthetic polymers or known molecular weight of carbohydrates. So you buy them, inject them, and then get the retention time. Then you plot a graph between log molecular weight versus the retention time. So you should get a nice line like this. So if you have an unknown system, you inject it, find out the retention time, and then you can, using this standard graph, get the molecular weight. This is the normal procedure which you use. So it is a very powerful standard graph which you can develop with known molecular weight standards. Let us look at a simple problem. I have two proteins, molecular weight of 2.5 into 10 power 5 Daltons and 1 into 10 power 4 Daltons. Now they are eluted out. The first one eluted out at a volume of 220 ml, second one is eluted out at a volume of 300 ml. Now I have another protein, I do not know the molecular weight of that protein, that elutes out at a volume of 270 ml at the same conditions. Now can you tell what is the molecular weight of that protein? So we can use this particular equation. If you remember, elution volume equal to A minus B log M. Why do you have a negative term here? Because as the molecular weight increases, the elution volume decreases, because as the molecular weight increases, the solute comes out faster, so the elution volume also decreases. So we have one equation, molecular weight of 2.5 into 10 power 5, elution volume is 220. Another equation, molecular weight of 1 into 10 power 4, elution volume is 300. So you substitute them, so you have two equations, two unknowns, A and B. One is this, B is the slope, A is the intercept. We can calculate A and B. Once you have calculated A and B, for an unknown protein we know the elution volume VE, so we substitute and we can calculate the molecular weight of the unknown protein. So it is very straightforward. So the values for A and B are given. So the molecular weight of the sample protein which is eluting out 270 ml is 3.35 into 10 power 4. Okay. So quite a simple problem. The problem is based on elution volume is a function of logarithm of molecular weight in a linear fashion. So you have a linear regression relation and you make use of the relation. So you need to know the elution volume for two proteins whose molecular weight is known. So once you know that, we calculate the slope and intercept of that regression relation, and for any unknown system, if you know the elution volume, you can calculate the molecular weight from that regression relation. So straightforward actually. Now in GPC we have to consider the weight, average molecular weight and number of average molecular weight, because if you have multiple components with the different molecular weights at different concentrations, then the weight average molecular weight of the entire mixture is given by this particular relationship. It is a summation of concentration of species I multiplied by the molecular weight of species I. So if you have 3 species with varying molecular weight M1, M2, M3 at different concentrations, that is C1, C2, C3, then what do? You do summation of C1 into M1 plus C2 into M2 plus C3 into M3 divided by C1 plus C2 plus C3. That is called the weight average molecular weight, where C is the concentration. Similarly, you can have number average molecular weight, that means you have the number of same species having a particular molecular weight Mi. So here Mn, that is the number average molecular weight, is given by summation of n, that is the number having this molecular weight Mi. So summation of Ni Mi divided by summation of Ni. So in polymer chemistry you have two types of molecular weights, one is called the weight average molecular weight, the other one is called the number average molecular weight. So this is the formula for calculating the weight average, and the bottom one is the formula for calculating the number average molecular weight. Okay. Now let us go to another type of chromatography. So far we spent considerable time on gel permeation chromatography. If you remember, we in the previous classes we talked about the reverse phase or hydrophobic interaction chromatography, then we talked about ionic interaction chromatography. Now let us go to affinity chromatography. This is also a very powerful tool, and it is based on the molecular recognition. That means if I have a protein, it will have a corresponding inhibitor which will have exact shape and size matching with the active site of this particular protein. So it is based on molecular recognition. So there is a target molecule which is complementary in shape and size. So it is exclusively used for protein and antibodies. So you can have a ligand and a protein binding, you can have a ligand and an enzyme binding, and this ligand could be very specific to the protein or the enzyme, whereas it will not be specific for any other protein or enzyme. So if you take a protein, it will have a ligand which will bind to only that protein, other ligands might not bind to the protein. So I can separate out ligands which will be very specific to this protein, and other ligands which are not specific to the protein will not get bound. So we can either immobilize the protein and the mixture of ligands could be passed, or we could immobilize the ligands and a mixture of protein could be passed. Okay, so the immobilization happens on a polymeric stationary matrix through covalent bonding. That is what we do actually. Okay, so how does it work? So again we have a stationary matrix and we have the affinity ligand anchored to the support. So you have a mixture to be separated, you have components which are complementary to the ligand and components which are not complementary to the ligand. So this is a mixture of protein, and only these proteins bind to the specifically to these ligands, whereas the other proteins are not complementary, so they travel down the column without getting bound. So what happens, only these proteins are enriched, the other proteins go out. Now how do you separate this protein? We change the buffer conditions, we change the pH, or we can change the temperature so that they get removed and they start traveling down. So we have on the inert support certain ligands anchored to the support. So proteins which are complementary to the ligands get bound, other proteins travel down, they get removed. So these proteins which are now bound can be removed by changing the buffer conditions, salt conditions or pH, so that they get removed and they get enriched here. Now again the column is ready for one more set of purification operation. This is how affinity chromatography works. So affinity chromatography depends upon the affinity between a protein and a ligand. So the protein could be immobilized on the support, so we can have a mixture of ligands flowing down, only those ligands which are complementary to the protein gets bound, whereas other ligands travel down, or we can have ligands bound to the stationary phase. So a mixture of proteins could be passing through, proteins which are complementary to those ligands get bound, other proteins travel downwards. So you enrich protein of our interest from a mixture of proteins. This is how affinity chromatography works, and the immobilization is generally done as a covalent type of bonding. So we have a matrix, we have the ligand, the protein which is complementary, which exactly matches in shape and size the active site of the protein, shape and size matches exactly with the ligand, so the protein gets bound here. You also have something called a spacer arm, so that the ligand is not very close to the matrix, So you may have interactions of the protein with the matrix which may disturb the selectivity pattern, that is why you have a spacer arm here. This is how a typical stationary phase will look like. You have a matrix, you have a spacer arm, and then you have the ligand. So the protein of interest will have a complementary shape and size of that of the ligand. Okay. So the spacer arm is used to ensure full accessibility of the affinity ligand. We do not want without the spacer arm the protein may come too close to the stationary phase, and it might not have good interaction with the affinity ligand, whereas you see in this picture because you have a spacer arm the interaction is better, whereas here in this case the interaction is very very poor. That is why you have a spacer arm here. So this affinity chromatography can be used for separating active biomolecules from denatured or functionally different forms of biomolecule. We can use it for isolating pure substances from low concentration. We can use it for removing specific contaminants. Okay. So you have toxic proteins, so if you have ligands which are very specific for the protein, then only those toxic proteins could be separated out. So affinity chromatography can be used for a wide range of purposes. It is very very expensive because you need to have a complementary protein or ligand, and then you need to immobilize that. So it is an expensive technique when compared to other techniques. So generally we use it for pharmaceutical products only and not for bulk chemical product. So what happens? A ligand interacts with the protein through a specific binding site. So you can have a binding of antigen to an antibody, we can have a substrate or an inhibitor or cofactor binding to an enzyme, a regulatory protein to a cell surface receptor. So there is a receptor in the cell surface, here is a protein which binds to that. So we can have an antigen antibody interaction or an inhibitor enzyme interaction or a regulatory protein cell surface interaction. So all these type of processes may be taking place during an affinity chromatography operation. So we can use any type of component as a ligand to purify its complementary binding partner. Okay. So you have a complementary binding partner and you have a ligand which is immobilized. So you can have a enzyme substrate analog, enzyme substrate inhibitor, cofactor, we can have antibody antigen, antibody virus, antibody cell, you can have lectin polysaccharide or lectin glycoprotein or lectin cell surface receptor, you can have a nucleic acid, you can have complementary base sequences, nucleic acid histones, nucleic acid polymerase or nucleic acid binding protein. If you have hormone vitamin, we can have a receptor or carrier protein. If you have glutathione, we can have a glutathione S transferase enzyme or GST fusion proteins. If you have metal ions, we can have polyhis fusion proteins, or we can have native proteins with histidine or cysteine. You can have tryptophan residues on their surfaces. So a large number of combinations of systems could be thought of. So depending upon what you want to purify and what you want to immobilize on the surface of the stationary phase. So what are the techniques used to disrupt this ligand protein interaction? So we have done a ligand protein interaction. Now we need to dislodge it, so that we want to collect it back or we want to regenerate the column. So how can we do that? We can change the pH condition, we can make it more acidic. This is generally used for protein or for antibody ligand affinity. So we change the pH so it becomes pH at 2 to 4, okay, or we can increase the ionic strength. Example, if you want to separate heparin, we can use specific eluents including the immobilized ligand or an analog in the free solution. So we can pass a free solution which will have the same immobilized ligand or a ligand which is an analog of in the free form. So we can use different combinations. So we can change the pH, make it more acidic, or we can change the ionic strength, or we can have a eluent which is analog, so that whatever has been adsorbed is removed. So all these techniques can be followed. Now we will look at further use and applications and techniques which we need to adopt in the affinity chromatography in the next class.